Thank you very much for inviting me. You will see it's very much on the experimental side as opposed to many of the theoretical works here. So this title really summarizes what my group in general is doing. So why main group, Redox Chemistries? So you will know that current lithium-ion batteries, at least at the positive side, rely completely on these four elements here. And so they bring along sort of all the troubles what we have, or many of the troubles what we have with lithium-ion batteries. It's in terms of price and ecological footprint. So and what we are trying to do is going for, to use the redox activity of main group elements around this group here. And what I want to speak about today is about oxygen and iodide redox chemistry, but also with implications for sulfur, what we're also working on. So why this is also interesting, apart from the ecological footprint of such batteries, if we were to exchange transition metals against main group elements, it's the potential for much higher capacity or energy density. And so one of these prime examples is using silicon as a host for alloying of lithium. And what you often hear in the first three sentences of the introduction of such a paper is like 10 times the capacity as opposed to a graphite intercalation anode. And this comes from this capacity of lithiating pure silicon. So this open symbol is the lithiation capacity of the delithiated phase. And this would be this closed symbol of the lithiated phase. No? And so depending on what phase you assume at the end, so like you can go up to lithium 4.2, you would get on the like 4,200 milliamp hours per gram of silicon, or on the vertical scale, this is per cubic centimeter of this phase. But the much more realistic measure is really towards the lithiated state. So we are already a lot closer to this typical family of intercalation materials, what we have now in lithium-ion batteries. But still, this is not the reality what we can gain, because such materials, they invariably always have very large volume changes. And so if you take into account this, because if you have a material which changes the volume a lot, you need to give it space to do so. And if you think of the whole thing not just as the formal host, but sort of a super host, which also gives space for volume expansion, then we end up with numbers like this, which already come a lot closer to what intercalation materials can do. But still, this is like a factor of 3, let's say. And we can do this with other main group chemistries like oxygen or sulfur. And this is a lot higher than, so this would be typical intercalation materials, like 1 is a typical cathode material, and carbon would be the anode material now. If we use the same elements to store sodium, then we again come a bit closer, but still the ecological argument remains. So oxygen redox is not an invention of mankind, so also life uses it to store energy all the way between molecular oxygen and oxide, no? And then via the intermediate steps of superoxide and peroxide. And we can do in a similar fashion, we can make, for example, alkaline metal batteries. You would typically have the alkaline metal negative electrode and a porous cathode where you form upon discharge, upon oxygen reduction, depending on which metal you're using, either the metal superoxide or the metal peroxide. In the aqueous case, it can be also the oxide. But there's another big topic in battery research regarding oxygen redox chemistry. It's in so-called lithium or sodium-rich layered oxides. What you would typically do in a current lithium-ion cathode is you just taking the redox activity of the transition metal. And the oxygen always remains in the oxide state. But if you align energy levels properly between the oxygen and the transition metal, you can also activate the redox chemistry of the oxide. So you can exchange electrons not just with the transition metal, but also with the oxygen. So, and this sort of doubles the capacity per gram of the total material. And this is a very, very active research field in lithium-ion cathode material or sodium-ion cathode materials. And then there's a sort of a hidden oxygen electrochemistry. Lithium carbonate is a very common interface component, and typically you want it just as a passivating agent, like let's say this would be your cathode material, and it will be covered by a very thin layer, like nanometers thin, of a carbonate layer. And if it's there, if it's thin enough, it can pass lithium ions through it. But if you charge, and this depends on the material, if you need to charge it higher than what is the thermodynamic stability of this is, then you're also exchanging electrons on the oxygen in the carbonate. So this would be hidden oxygen electrochemistry. So in general, with such main group elements, what we very often encounter is that we have electrochemistry with insulators, which obviously doesn't go together very well. No? And so, for example, in the case of metal oxygen cells, we are forming as a discharge product here the peroxide. This can go via a different mechanism. I come back to this. But we encounter this very generally in main group elements, so for the oxides, peroxide, superoxide, or even the oxide can be involved in metal oxygen cells. But when it comes to sulfur chemistry, we are dealing with sulfide and sulfur, so we need to interconvert them electrochemically, so we need to exchange electrons. Or also you can think of magnesium sulfur, aluminum sulfur batteries, or iodine. There's the one central hurdle, and there's always the question how to transfer electrons with more than just sort of monolayers of such materials. So we want large amounts of materials to have large capacities. And so another central hurdle is parasitic chemistry. You have this also quite generally, but here for the example of oxygen. So this would be the ideal cell reaction, let's say from oxygen to superoxide or peroxide, and of course this directly establishes the stoichiometry that we would find. And so we can take the discharge product yield relative to the electrons, or on recharge, how much oxygen we get out as a measure of parasitic chemistry. And what, for the example of alkaline metal oxygen cells, what we find as a pattern is if we take potassium, we have close to ideal yields of both on discharge and recharge. And as we go in this direction, we are getting worse. And as we go from superoxide product to peroxide product, is also worse. And so, of course, people were thinking of what's the reason for this. And so this comes back to the sort of known steps in the reaction mechanism. We have you see this parasitic chemistry, for example, here on discharge. So this would be the ideal stoichiometry, so this diagonal line of 2 electrons per oxygen converted. But what we see typically per oxygen consumed, we have this ratio of 2, but there is less peroxide forming, and on recharge it's even worse. So the red curve here is how much peroxide is consumed, so that means also electrons, so this is not on the ideal line, so all electrons are consumed into non-ideal reactions, and again there's less oxygen coming out than expected. And so people thought it's some intermediate in the reaction mechanism, which could be superoxide, which is a strong base, a nucleophile, and this was always the common understanding that this is the reason for it. But then theoreticians came to help, and they calculated, so what's the reaction energies of like a typical solvent moiety, like an ether, with any of those compounds that we find, either intermediates or final products. So this can be the nucleophilic substitution, or H-atom abstraction, or proton abstraction. And what they always found, very high, prohibitively high activation energies, and everything is endothermic. And so I thought it must be a different reactive species, which could be singlet oxygen, which is the first excited state of molecular oxygen. And why this hasn't been looked at before, it's simply experimentally difficult to to analyze in this type of system. So we have two possibilities. The one is direct detection of the characteristic wavelengths of 1270 nanometer, which when you have singlet oxygen in a condensed medium, then it will spontaneously decay and emit these wavelengths. But it's quite insensitive to measure. Still, we were able to do this, and we could see that at least on charge, we could see significant amount of singlet oxygen. So this is the very direct proof. But we wanted something more, first easier to use and more sensitive. And so the other way is this, that we expose a trap for singlet oxygen, which has to be selective and stable and sensitive and so on, so which was quite a difficulty to find, but we found something. And so then when this reaction happens, then we can look at disappearance of this or appearance of this by various spectroscopies. And so by establishing these tools, then we looked in many aspects of singlet oxygen in non-aqueous electrochemistry. So first we found that it's actually the problem and not superoxide or peroxide. Then also we have shown that lithium carbonate is a very dangerous agent actually in batteries. It's very common but very dangerous really when it comes to higher voltage cathode materials. Then material stability against this singlet oxygen. Then we have shown various types of quenchers, how they can act. Then we looked very closely into the formation mechanism. I'm going into this, showing a few details about this, how it's actually forming. And then about mediators. So this is mediators are used in metal oxygen chemistry to deal with this other hurdle, which is the insulators. But people thought, yeah, it's all fine if we use mediators, then it's easy. But actually, they can be also very dangerous. And so we looked at reaction mechanisms in this respect. And then the other thing is what we are working on now is singlet oxygen in relation to these oxygen redox intercalation materials, because they are also found to have very highly reactive surfaces with the electrolyte, and part of it may come from this. So let me go a bit through those two works about formation mechanism. So just to remind, so this is the pattern what we find. So if we with potassium, we are sort of safe, but as we go towards lithium, it's becoming worse, and as we go from superoxide to peroxide, it's again worse. So this, of course, doesn't fit with the notion that it's coming from superoxide. But how we approach this, so looking at the thermodynamics of superoxides and peroxides in combination with possible cations. And what we find here, so like on a M plus potential scale, so this would be the lithium plus scale. So the oxygen superoxide couple would be around here. Peroxide is higher, so that means it's thermodynamically more stable, so which means superoxide in the presence of lithium ions will spontaneously go to peroxide. For the sodium case, the difference is not big, but still superoxide will spontaneously go to the peroxide. For potassium, it's the inverse. So if we have potassium superoxide, it will be stable, and that's why you can buy it in a bottle. And actually, the potassium peroxide is the less stable. So we have seen, so the chemistries which perform badly are here. So where disproportionation can happen, and where no disproportionation is to be expected, it's safe. And so we looked at what happens if we expose superoxide to any of those cations. And we measured quantitatively the yields of the reaction. So we should get per 2 superoxides, we should in a disproportionation reaction, 1 peroxide plus in conjunction with the cation plus molecular oxygen. And so we measured all those, the yields of those. And so we measured the triplet oxygen yield, singlet oxygen yield, and the peroxide. In the case of pure lithium, we found this, so it's a little bit of singlet oxygen, and sort of by this fraction we get a reduced amount of peroxide. And if we add like a weak Lewis acid, so these are the typical cations of ionic liquids, which often are thought to be very attractive electrolytes, and they also have been looked at in the in context of metal air batteries. If we have a weak Lewis acid cation present, then it's becoming a lot worse, so the singlet oxygen yield goes up, and triplet oxygen and peroxide goes down. And so we can sort of rewrite this equation, so we are getting as much peroxide as triplet oxygen, and what is missing here is singlet oxygen. We actually don't know why we lose the peroxide. So this is, I think we sort of need to approach this by theoretical means, but why we lose triplet to singlet oxygen, we looked at theoretically. So this is made by some colleagues from Rome and Sorbonne in Paris. So we looked at the reaction energies of two lithium superoxides going via a triplet pathways towards first this would be molecular species in solution, and then towards solid peroxide. So the main driving force is really forming the solid peroxide, and there's just a little activation energy here. But for the singlet pathway, which should yield the singlet oxygen, there is quite a big barrier of like an electron volt. And so this explains why if we expose superoxide to pure lithium electrolyte, we're getting quite little singlet oxygen, but mostly triplet oxygen. And so why in the case of weak Lewis acid we get so much more singlet oxygen? So the explanation we came up with is, so if you have a mixture of a weak Lewis acid and the strong Lewis acid lithium plus, then you may think of part of the superoxide is associated with the lithium and part is sort of the free superoxide. And then we may have a singlet adduct, which still has is an anionic species, and then we over the entire pathway we just have the highest barrier is simply lower, and so we can overcome this barrier, and that's why the singlet yield is higher. So by this we can revisit the previous thoughts of what the reaction mechanism is. So people always thought that the first intermediate superoxide can either be reduced further or disproportionate, and the return on reoxidation. So first we would extract an electron from the peroxide to form a superoxide intermediate, and this people thought this could be further oxidized, but we really came to the conclusion that the second electron transfer is always and sort of purely disproportionation. And this becomes problematic if we know that disproportionation is always prone to give the singlet oxygen. And then the other major hurdle is insulators. So a couple of years ago we have first shown that we can actually use organic redox mediators to reoxidize peroxide. So because you would have, at the end of discharge, you would have like structures of hundreds of nanometer large lithium peroxide, and this is way too insulating to really oxidize this by so the far pieces of it via electron transfer through the peroxide. So if we have a mobile mediator in the solution, which we oxidize at the surface, this can then oxidize the peroxide in remote places and then evolve oxygen. And so if without this mediator you would get to very high charging potential, and with the mediator you would nail down the charging potential to the redox potential of the mediator. So there people looked in many variants of this, and so what they always thought is always, so what the mechanism is, quite naively I would say then that you simply have peroxide, which is a 2 electron reduction products of the oxygen. You need 2 oxidized mediators with 1 electron each, and then you have sort of the 2 electron mechanism, which is quite unlikely. So what's the relation to the singlet oxygen here? One may come up with sort of a threshold when you do a a 2-electron oxidation. So we know we have a 1 electron volt difference between singlet and triplet. So if it's a direct 2-electron oxidation, we would divide this by 2, and we would end up with sort of a threshold around 3.5 volts, if it were a 2-electron oxidation. We looked then closely into this mechanism. So first we have shown that this, of course, the direct concerted 2-electron mechanism is not happening, extremely unlikely. What really happens is a first equivalent of mediator forms first at the surface, so you need to think of this as being a solid particle. We are forming first at the surface a superoxide species, so we are extracting lithium ions and electrons, but this is then we have a lithium deficient surface. This will have then a redox potential around here. And then in a second step, we may then transfer a second electron, so to oxidize this surface superoxide to oxygen. And for this process, if we add the 1 electron volt, we would end up with a threshold for singlet oxygen evolution above 3.5 volts. And the other possibility is that the surface superoxide species disproportionates, and there we know already it's very prone to form singlet oxygen in any case. No? So we didn't shy back of any effort here, so we took quite a number of redox mediators which cover the entire voltage range between this equilibrium potential of the oxygen peroxide couple, all the way well above this threshold which you could think of. No? So this threshold would be here, so we took quite a number of mediators. With those, we first determined the singlet and triplet oxygen yields. I must say here that the quantification of singlet oxygen is not as good as the quantification of the triplet oxygen, but anyway it gives a good measure of it. So we see 3 groups, some at low voltages, which you could think of low voltage is gentle, is not the case. Intermediate voltages, they are sort of good, and at high voltages, then they evolve a lot of singlet oxygen. And so to nail down the mechanism here, we measured kinetics. So kinetics we can think of, so the first would be sort of apparent kinetics between oxidized mediator exchanging charge with the solid surface. A second one, once we have a superoxide surface, a second electron transfer to evolve oxygen. And then a third one would be disproportionation kinetics. So these are the kinetics we measured for those 2 processes. So this is the peroxide oxidation in the first step. It's giving this, so this parabola-shaped dependence on driving force. Also for the superoxide oxidation, we get this. And so this is the unexpected thing was here, that as we go beyond a certain driving force, like here or here, the kinetics goes down, and this is the electrochemists amongst you will recognize here the Marcus inverted region, which was quite astonishing and also exciting to us to see this. Because as far as we know, it's the first case that this has been shown for heterogeneous systems with insulators. And also we measured disproportionation kinetics, and we found this is always higher than any of these electron transfer kinetics, or higher than most of those. So, and since disproportionation is faster than any of the electron transfers, it's also important to look at what the disproportionation yields in which type of oxygen. And as I've shown before, that this is the yield of disproportionation to a singlet or triplet depends on the weak Lewis acid, on the presence of weak Lewis acids. So you may take the equilibrium potential of the mediator, so the oxidized form of the mediator is always a weak Lewis acid. You may take this as a proxy of the Lewis acidity, and we see also a trend in this. And so this would be the overall mechanism. So after first oxidation step to a superoxide intermediate, then we have 2 branches, disproportionation or a second oxidation, which is controlled, so the kinetics is controlled by Marcus theory, in fact, which finally gives then the ratio of which oxygen form we are emitting. So in the first step is the rate limiting step, and disproportionation is again the major oxygen evolving pathway. And in order to compete with this, one needs to look to be faster than the disproportionation pathway. So then shift to other work in structural evolution. So we are dealing with insulators, and when we discharge such cells or also recharge for sulfur, we need to electrodeposit insulators, which is again sort of a self-contradicting thing. And so the easiest thing to think of how lithium peroxide forms would be to form superoxide and then to further reduce it, and then you get an insulating layer, but this would be just a few nanometers thick. But what one finds is sort of large structures, and this must form via a solution mechanism which has mobile intermediates. So the previous thought was that depending on the electrolyte, this would go either this pathway or this pathway, and so we wanted to look at this closer, and for this we developed a method based on in situ SAX and wax. So we made an in situ cell which we put in a in-house SAX machine here. And the electrolytes we used for this sort of prototypical cases, what people thought would either form a surface layer or like larger particles, so like a low donor number or high donor number solvents which go either in this direction or in this direction. And why we use SAX is because these are like feature sizes of like hundreds of nanometer large, and one knew already that there are lamella forming of some a few nanometers thick, so this is just the right range for small angle scattering. And so for these two extreme electrolytes, we see different features in the SAX pattern. And in terms of the discharge capacity, we see just quite the opposite of what has been expected by previous thinking of what the two electrolytes do. And so it must be related to different pore filling and then peroxide structure. And so you see here the SAX curves, they're sort of quite featureless, but in order to get good insights out of it, we need to advance with data analysis. So what we did here is making a representative model of this 3D carbon structure, and in this we took models to grow different morphologies of the lithium peroxide. So this finally gives then morphologies of electron density contrast, which is the origin of the scattering pattern. And so we can then adapt the model in a way that the experimental scattering pattern and the modeled one fit as closely as possible. And so what we get from this is real space peroxide morphology. So this is not an illustration. This is like we used a growth model to grow this disc-like, parallel disc-like features. And so this is an output of it, real space morphology. And then as we have a growth model, so we have nucleation and growth rates. So and for these two cases, we get then different best fit structures. These are like smaller platelets and more of them stacked, and this fits with what you see in the electron microscopy. So this is actually stacked plates. And in the other case, the best fit model predicts a few layers but largely extended, and this is also what we see in the electron microscope. And so then we also challenge the view that there is direct second electron transfer, so to have a surface growth. And so we also performed this at conditions where people thought there is definitely surface growth, so second electron transfer. So this is high overvoltages, very high currents, also in this electrolyte. And what we find is this pattern, and we simulated artificial surface growth and the SAX pattern of this, and this can by no means be related to this, what we find. So we finally can say that there is by no means any surface mechanism, and all the second electron transfer is always a disproportionation step. And we are currently looking into sulfur electrochemistry, which is a very promising battery chemistry, and there you have a similar mechanism both on discharge and charge. So on discharge you're forming lithium sulfide, on charge you're reforming solid sulfur. And also there, our current understanding is that the last electron is always transferred by disproportionation. So we also took this in situ Sachs for iodide-based supercapacitors. So what people thought there is, so you can augment the capacitance of like the positive electrode of a supercapacitor by adding iodide, which then is oxidized to the triiodide. So you have redox capacity on top of the pure capacitance, the double layer capacitance. And so this was the thinking that what you can do is up to the I3 minus. So we took this to both in situ Raman and Sachs, and this is how the electrochemistry looks like. So you have at a certain voltage range, you have pure electrochemical capacitance, and then you have redox capacity. So translated this on the time trace, and then this is the small and wide angle scattering pattern. We see over these 2 cycles there is some reversible formation of something, both in the wide angle, so here like 3 peaks, and in the small angle we have features. And we can associate this with a large amount of solid iodine forming, so not just the triiodide which would remain in solution. And the implication of this is that solid iodine has a much higher redox density per unit volume. And on top, this is possible very fast. So, so up to like a current, so this current of beyond 1 amp per gram. So this would be a full cycle within less than a minute. And so almost all the capacity can be used in this with a solid product in such a fast cycling. And also always a concern of supercapacitors is self-discharge. Also this is in a reasonable range. So with this to summarize, I've shown some work on redox mechanism with oxygen. And so the main 2 concerns there are really that it's disproportionation which gives singlet oxygen, and this is also what we find in mediated oxidation. And then we, over the last years, we developed Sachs as a powerful tool for electrochemistry where we have phase formation or phase changes or morphology changes. And like here the 2 examples of oxygen electrochemistry and here iodine electrochemistry. And so with this I come to acknowledgement, the ESE and then the Austrian funding agency, and thank you for your attention.
Thank you for this nice insights into the chemistry or electrochemistry of new batteries. For the questions, please wait till you get the microphone. So, other questions, Uli?
Yeah, thank you very much. I have lots of questions because I'm not so familiar with these things. But so actually, maybe I don't know if I have 3. So the first one, if this, so how do you know if it's singlet or triplet? Do you have any experimental evidence for what you have?
Yes. So this trap that we use is only it's only binding to singlet oxygen and not triplet oxygen, and so it's an anthracene.
Okay, so you have another. May I suggest XPS because they can very clearly see the difference actually.
Between the singlet and triplet?
Yes, yes, yes.
Would you see this, the gas,
yes,
it's gas phase?
No, on surfaces. You can see that very clearly actually. So.
And would it remain on the surface? Because you need to form it in a...
Yeah, as it adsorbed on the surface.
Yeah.
Okay. Mm-hmm. Okay. So you studied in the gas phase with, so...
No, it's in solution phase.
In the solution, okay.
And so to make sure that this probe is sensitive or selective to singlet oxygen, so we made the singlet oxygen by the normal route by photosensitization.
Okay.
And then with light, then it forms this adduct, and without light, it does not.
Mm-hmm. With light, okay.
Yeah.
Well, maybe we can discuss later. The second question was, maybe I got it wrong, but somehow I immediately when I see this lithium oxide something that the humidity should play a role, but somehow you said it doesn't, or maybe this is just because you do everything in this dry box with whatever ppm humidity, or, but under normal circumstances, does it play a role?
It does, but it's astonishingly robust against water, so you can put thousands of ppm of water and you can still form the peroxide.
Okay, okay.
But the parasitic chemistry is influenced by it.
Okay.
So you cannot do it for completely ambient conditions. That doesn't work.
And the third thing was, I mean, you had these very featureless Sachs curves, right? And then you came up with a model. I mean, can you come up with like any model?
No, I mean, of course. So for the Sachs that you can interpret it, you should always have also real space information. So and we had real space information both from electron, also TEM and SCM, and then with this we had one can narrow down the possible structures, and but the other possibility what people thought is just conformal coating, and we simulated this, and this doesn't happen. But it, I mean, other things could be like just spheres distributed, but this also doesn't fit. It's of course not unique, but one needs complementary information to have a real space information, and then one can approach the thing. But yeah, of course one needs to be careful because you could fit many things. Yeah.
Okay. Yeah. Alexander.
Maybe I missed it, but I was wondering why some of your redox mediators do not allow for disproportionation. How is that? No, what is the common ground for those who don't allow disproportionation?
They all allow, or from which data did you
There was this slide where you had the redox potential for the redox mediators versus the amount of singlet and triplet oxygen produced. And there was a bunch in the middle that had absolutely no singlet oxygen.
No, I mean, they still do.
So you just don't trap it?
There we were not sensitive enough to detect singlet oxygen, so at least our method to detect it did not detect this, and also the triplet oxygen is a bit less than what it should be. So there might be still a bit, and we would also expect it because there's always you see that none of the mediators except for one single one none of them is competitive against the disproportionation kinetics. So you would always expect a bit. And the other thing is the mediators around here, they are relatively good quenchers. So it's, I have illustrated this here. So you have here the formation pathway, and on top of this you always have a quenching pathway, which the mediators are, some of them are quenchers. So, but the lower the voltage of them, they are better quenchers, because you need partial electron transfer for the quenching mechanism. And so those around here, so the lower you go, the better quenchers they are. And that's why it's a combination of all those processes which then determine the relative yields of which oxygen we get.
Let's thank the speaker again.